Right. Here's a question that I guarantee you have never properly sat down and thought about. The ocean is salty. Obviously, everyone knows that. But why? Where did all that salt come from?
It sounds like the kind of thing you'd figure out in about 30 seconds, doesn't it? And then you actually start thinking about it and you realize, hang on, I have absolutely no idea.
Exactly. And here's the thing that makes it even stranger. Rivers feed into the ocean constantly, billions of liters of fresh water pouring in every single day. And yet, the ocean stays salty. It doesn't dilute, it doesn't get less salty over time.
Which means something is keeping it salty. Something is adding salt just as fast or even faster than fresh water is arriving.
And when you start pulling on that thread, you end up somewhere completely unexpected. You end up at volcanoes, at ancient rocks, at the fact that the ocean has been going through a kind of planetary recycling system for 4 billion years.
So let's get into it. Why is the ocean salty?
Okay, so the first thing to understand is what we even mean by salt. When most people say the ocean is salty, they're picturing table salt, sodium chloride. And that is the biggest component. About 85% of what's dissolved in seawater is sodium chloride.
But there's also magnesium, sulfate, calcium, potassium, all these other minerals swirling around in there. The ocean is basically a mineral soup, just a very, very large one.
The average salinity of the ocean, how salty it actually is about 35 grams of dissolved salt per liter of water, which doesn't sound like much, but think about it this way. If you evaporated all the water out of all the world's oceans, you'd be left with enough salt to cover every continent on Earth in a layer about 160 meters thick.
160 meters? That's taller than the Shard.
Almost. The Shard is just over 300 meters, but yes, the salt layer would be roughly half the height of the Shard, stretching across every land mass on the planet. It's a staggering amount of material.
So where did it all come from? Because the Earth had oceans before it had that much dissolved salt. Early Earth's oceans were probably much less salty and possibly even slightly acidic.
Right. The short answer is it came from two main places: the land, via rivers, and the ocean floor, via volcanic activity. And those two sources have been working in tandem for billions of years.
Let's start with the rivers, because that's the one most people have sort of half heard of.
So, rain falls from clouds, and before it hits the ground, it's already doing something chemical. It's absorbing carbon dioxide from the atmosphere, which turns it into a very weak carbonic acid. Not dangerous, but enough to be reactive.
And then this slightly acidic rain hits the rocks, and over time, slowly, patiently, over millions of years, it starts to dissolve minerals out of those rocks. Calcium, sodium, potassium, all of it gets picked up and carried into streams, into rivers, and eventually into the ocean.
This process is called chemical weathering, and it has been happening since the Earth had rocks. Every river on Earth is carrying dissolved salts towards the sea, right now. The Amazon, the Nile, the Thames, all of them are transporting dissolved salt into the ocean.
But here's the thing, rivers aren't salty. You can drink river water within reason, ignoring the other stuff that's in there. So how are rivers adding salt to the ocean if they're not salty themselves?
It's because the concentration is so low in rivers that we can't taste it. The Mississippi River, for example, carries about 2 million tons of dissolved minerals into the Gulf of Mexico every single year. 2 million tons. And yet its salinity is only about 1/10%, completely undetectable to human taste.
But the ocean is massive, and those minerals have been arriving for 4 billion years. They accumulate.
And crucially, when water evaporates from the ocean surface to form clouds, the dissolved minerals don't evaporate with it. The water molecules escape, the salt stays.
So you get this one-way ratchet. Fresh water in, fresh water out via evaporation, but the salt just stays, builds up, concentrates.
Which is why, if you think about completely landlocked bodies of water, lakes with no river outlet, they can get extraordinarily salty. The Dead Sea is one of the most famous examples. It has a salinity of about 34%, compared to the ocean's 3.5%. almost 10 times saltier.
Which is why you float so effortlessly in the Dead Sea. The water is so dense from all that dissolved salt that the human body just bobs on the surface. You can sit there reading a newspaper, which is one of the more surreal travel photos people bring home.
And the Great Salt Lake in Utah works on the same principle. No outlet, water evaporates, salt concentrates. It's currently somewhere between 3 and 9 times saltier than the ocean, depending on water level.
Okay, so that's the river explanation. Minerals dissolving out of rocks, carried by rivers, accumulating over billions of years. But you mentioned a second source, the ocean floor itself.
This is the part that took scientists much longer to figure out, and honestly, it's extraordinary. So the ocean floor isn't static. It's being constantly created at places called mid-ocean ridges. Long underwater mountain ranges where two tectonic plates are pulling apart and molten rock from deep inside the Earth is bubbling up to fill the gap.
The Mid-Atlantic Ridge is the most famous one. It runs almost from pole to pole down the middle of the Atlantic, and it's been creating new ocean floor for hundreds of millions of years. Iceland is actually sitting right on top of it, which is why Iceland has so many volcanoes and geysers.
Now, at these ridges, seawater seeps down through cracks in the newly formed rock. It gets heated, dramatically heated, by the magma below, and as it heats up, it reacts with the rock and picks up new minerals: iron, manganese, zinc, copper. Then it comes shooting back out through structures called hydrothermal vents.
Hydrothermal vents are one of the most dramatic things on the ocean floor. They're basically underwater geysers. Some of them, called black smokers, shoot out water at over 400 degrees Celsius, which would normally boil instantly, but the pressure down there is so extreme that it stays liquid.
And these vents were only discovered in 1977. A research team from Woods Hole Oceanographic Institution in Massachusetts was exploring the Galapagos Rift in a submersible called Alvin when they suddenly came across these columns of superheated, mineral-rich water billowing up from the seafloor. They described it as looking like black smoke rising from chimneys.
And around these vents, completely unexpectedly, they found thriving ecosystems, entire communities of organisms, giant tube worms, blind shrimp, ghostly white crabs, all living in complete darkness with no sunlight, surviving on the chemical energy from the vents.
It was the first ecosystem ever discovered that doesn't depend on the sun. It rewrote our understanding of where life can exist. And it's part of the reason scientists now think there could be life in the oceans of Jupiter's moon Europa, which is covered in ice but almost certainly has a liquid ocean beneath, possibly with hydrothermal vents on its floor.
We genuinely might find life on another world and trace it back to a process that's also explaining why Earth's ocean is salty. That's the kind of connection that keeps you up at night.
So the vents are adding minerals to the ocean, but they're also removing some. The seawater that flows in and reacts with the hot rock loses certain minerals in the process, particularly magnesium. So the vents are acting as a kind of chemical exchange system, not just adding stuff, but also filtering.
Which brings us to something that genuinely surprised scientists when they worked it out. The ocean's salinity, how salty it is, has been remarkably stable for a very long time. It's not just endlessly accumulating. There must be processes that remove salt as well. Otherwise, the ocean would just keep getting saltier and saltier until nothing could live in it.
And those removal processes exist. When seawater gets trapped in marginal seas, shallow areas near coastlines, it can evaporate completely and leave salt deposits behind. These are called evaporites, and there are massive ancient evaporite deposits buried under places like the Mediterranean Sea and the Gulf of Mexico. Evidence of ancient oceans that dried up and left their salt behind.
There's also a process at mid-ocean ridges where certain minerals get absorbed back into the new rock, and salt gets buried in ocean sediment. So you have salt coming in from rivers and vents, and salt going out through evaporation and burial. And over geological time, these have more or less balanced out.
It's a planetary homeostasis. The Earth has been regulating its own ocean chemistry for billions of years. Not perfectly, not without fluctuations, but well enough that the ocean hasn't become a lifeless brine or a flat freshwater lake.
Now, there's a question that comes up whenever this topic gets discussed, and it's one that seems obvious but actually has a surprisingly complex answer. Why are lakes mostly fresh, but oceans are salty?
Because most lakes have outlets, rivers that drain them, so the water flows through, taking dissolved minerals with it, and the lake doesn't accumulate them. The Great Lakes in North America are a perfect example. Billions of tons of water moving through the system, but because it keeps moving, the minerals don't build up.
The ocean, on the other hand, has no outlet. There's nowhere for the water to go except back into the atmosphere as water vapor. So the salt stays.
There's actually an interesting thought experiment that scientists have considered. If you took the ocean and connected it to some enormous drain, some way to let the water flow out without the salt, eventually you would concentrate it into something far saltier than the Dead Sea, a thick, mineral-rich brine covering the ocean floor.
Which is roughly what would happen to Earth if we lost our atmosphere and the water started escaping into space. Mars may have gone through something similar. There's strong evidence that Mars once had liquid water, possibly even oceans, and some of that water is thought to have been lost to space over billions of years.
There are salt deposits on Mars that scientists believe were left behind by evaporating water. Studying Martian geology is, in a strange way, like getting a preview of a future Earth or a glimpse of an Earth that might have been.
Let's talk for a moment about how the ocean's saltiness affects life, because it's not just a background detail, it's fundamental.
The salinity of the ocean has shaped the entire history of life on Earth. The first complex life evolved in the sea, and those organisms built their biology around seawater. Which is why even today, the fluid inside our cells, the salt concentration in our blood and our tears, is remarkably similar to ancient seawater.
Your blood has a salinity of about 9 grams per liter. Ancient Precambrian seawater, the ocean as it was when our distant ancestors first evolved, is thought to have had a similar salinity. We are, in a very real sense, carrying the ancient ocean inside us.
The marine biologist Rachel Carson, who later became famous for Silent Spring, wrote about this in her 1951 book, The Sea Around Us. She described how life, in moving from the ocean to the land, essentially had to bring the ocean with it, sealed inside its own tissue.
Which is why when you cry, your tears are salty. When you sweat, it's salty. When you get a cut and taste your own blood, it tastes of the sea, because in a very literal sense, it is.
Now, the ocean isn't uniformly salty everywhere. Different parts of the ocean have different salinities, and this matters enormously for ocean currents and weather.
The Atlantic Ocean, for example, is slightly saltier than the Pacific. Partly because the Atlantic loses more water to evaporation. There's a lot of evaporation over the tropics. And partly because there's a flow of relatively fresh water from the Pacific into the Atlantic through rainfall patterns over Central America.
This difference in salinity helps drive the Atlantic Meridian overturning circulation, a massive system of ocean currents that includes the Gulf Stream. The Gulf Stream is what keeps the United Kingdom and Western Europe so much warmer than they would otherwise be. London is at the same latitude as parts of Canada that get brutal winters, but London gets rain and mild temperatures, not -30.
And the driver of that entire system, in part, is salt. Dense, salty water in the North Atlantic sinks because salt water is heavier than fresh water. When it sinks, it creates a kind of conveyor belt, pulling warm surface water up from the tropics to replace it. That warm surface water is what keeps Western Europe habitable.
Which is why climate scientists are concerned about what happens if Greenland's ice sheet melts significantly. All that fresh water flooding into the North Atlantic would dilute the saltiness, reduce the density difference, and potentially slow or even collapse the overturning circulation.
If that happens, Europe's winters could become dramatically colder, even as the rest of the world warms. It's one of the more counterintuitive potential consequences of climate change, parts of Europe getting much colder because of global warming.
There's actually historical evidence that something like this has happened before. About 12,900 years ago, at the end of the last ice age, a massive lake of meltwater, Lake Agassiz, covering much of modern Canada, catastrophically drained into the North Atlantic. The influx of fresh water appears to have disrupted the ocean circulation and triggered a sudden cold snap that lasted about 1,200 years. Scientists call this the Younger Dryas.
Temperatures in parts of Europe dropped by as much as 15 degrees Celsius within decades. Forests retreated, glaciers advanced, and it appears to have happened almost overnight in geological terms, a single catastrophic drainage event reshaping the climate of an entire hemisphere.
All because of salt, or rather because of the sudden removal of salt from a critical part of the ocean.
So we've gone from why is the ocean salty to the answer is volcanoes, rocks, and ancient rivers to the salt in the ocean is keeping Europe warm to a prehistoric flood nearly froze the continent. This is what happens when you pull on a thread.
One last thing before we wrap up, and this is the thing that always catches people off guard. Scientists actually don't know exactly how old the ocean's current salinity is, or whether it has always been at this level.
The best estimates suggest the ocean has had roughly similar salinity for at least 500 million years, possibly much longer. But the exact balance between inputs and outputs has varied. There have almost certainly been periods when the ocean was saltier and periods when it was less so.
And there are still significant unknowns. The role of hydrothermal vents wasn't even understood until 1977. Before that, scientists had only part of the picture. It's possible there are other removal mechanisms we haven't fully accounted for.
The ocean covers 70% of the planet's surface and reaches depth of nearly 11 kilometers. The deepest point, the Challenger Deep in the Mariana Trench, is so far down that if you dropped Mount Everest into it, the peak would still be over 2 kilometers underwater. And we have better maps of the surface of Mars than we do of the ocean floor.
Which means the full story of the ocean's salt is still being written. Scientists are still down there, in submersibles and with remotely operated vehicles, finding new vents, new ecosystems, new pieces of the puzzle.
And every time they find something new, it changes the picture slightly. That's one of the things I love about this kind of question. It sounds simple, why is the ocean salty? And it opens up into 4 billion years of planetary history, evolutionary biology, and the future of Europe's climate.
The short answer is rocks dissolved by rain, carried by rivers, accumulated over billions of years, combined with minerals pumped out by underwater volcanoes, all held in place because the ocean has no outlet, only evaporation.
But as we've seen, the short answer is just the beginning.
Absolutely. And on that note, thank you so much for listening to the why behind everything. If you've been enjoying these episodes, please do subscribe on YouTube. It genuinely helps us keep going and reach more curious people like you.
And next time, we're asking another question that sounds simple until you really think about it. Why do we wear wedding rings on the left hand? It involves ancient Romans, a belief about a vein running directly to the heart, and a small but fascinating argument about which hand we've had it wrong on this whole time.
Don't miss it. Subscribe, and we'll see you next time.